Yes. So in this session, we are going to have the best fitted curve as a parabola to a bivariate data using the method of least squares again. As we have seen in our previous sessions, we have obtained the best fitted straight line, which is also known as the equation of regression equation of straight line to a bivariate data. Now in this session, we are obviously utilizing the method of least squares. In this session, we are going to extend that one by utilizing the method of least squares. We are going to fit a parabola to a given bivariate data, right? So in a bivariate data, as we have seen earlier also, there are two variables to be considered. One is the independent variable x1, x2, xn if the data contains n number of entries, and the dependent variable, that is y1, y2, yn, right? So now the next is the curve that we have taken is the parabola to get the best fitted parabola in the bivariate data. And accordingly, we have taken the general equation of parabola as fx equals to a plus bx plus cx square. Now, according to the previous session, what we need to do is, as the method of least square suggests, we need to obtain the minimum distance, sum of the squares of the minimum distance from the given bivariate points to the curve which is taken as the best fitted curve, that we have taken the parabola as a plus bx plus cx square. Now in this best fitted parabola, the unknown quantities are a, b and c. So minimizing d, that is the distance from the bivariate data to this parabola, minimizing the distance, we will be obtaining three equations with the three unknowns a, b, and c, and solving those equations, we will be getting the values of a, b, and c, and that will be the best fitted parabola. And then a plus bx plus cx square will be the best fitted parabola to the given bivariate data, right? So let us proceed on for that. What we need to do is, we need to take the minimum of the sum of the squares of the distance from each of the bivariate point to the parabola we have taken, general equation as a plus bx plus cx square. So I'm writing the minimum of d. What this d is the distance from the curve to the bivariate points. So that will be taken as yi minus a plus bxi plus cx square xi square whole square, sum of the squares of these distances, and we will be taking minimum of this. So now taking minimum of this, since the unknown quantities here are a, b, and c, so we will be differentiating first with respect to a. That means we will be finding del a of d, or we will be equating del a of d to 0, equating this del a of the distance, where sum of the squares of the distance to be equal to 0, we will be getting it as 2 times of summation yi minus a plus bxi plus cxi square. And as it is with a, and a has the only coefficient -1, so -1 equating to 0. Now simplifying this, we will be getting it as summation yi minus a summation over I 1 minus b summation xi minus c summation xi square equals to 0. So next is, we can write it as a and 1, summing it up n times. So obviously it will be an. So simplifying this, we can write it as summation yi equals to an plus b summation xi plus c summation xi square. So this is the first equation we will be getting by taking the derivative with respect to a to be equal to 0. Now in the next part, we will be taking it as del B, differentiating with respect to B and equating it to 0. We will be getting it as, again twice, summation yi minus a plus bxi plus cxi square. Obviously, when differentiating with respect to b, the coefficient is minus xi, so that coefficient will come out minus xi and equate it to 0. So after simplifying, we will be getting it as summation yi xi minus a summation xi minus b summation xi square minus c summation xi cube equal to 0. So we can write it as summation xi yi equals to a summation xi plus b summation xi square plus c summation xi cube, and this total thing will be, this is our the next equation, second equation. And then again taking differentiating with respect to c, del c of d, equating it to 0, we will be getting it as twice summation yi minus a plus bxi plus cxi square, multiply it with, as c, the coefficient of c is xi square, so minus xi square, and equate it to 0. So we will be getting it as, simplifying, summation xi square yi minus a summation xi square minus b summation xi cube minus c summation xi to the power 4 equals to 0. And we can write it as summation xi square y equals to a summation xi square plus b summation xi cube plus c summation xi to the power 4. So this is the third equation we will be obtaining. And these three equations are nothing but the normal equations for the best fitted parabola to a bivariate data. So in this way, utilizing these normal equations, we can find the three unknown quantities, value of the three unknown quantities, A, B, and C. And after getting the three unknown quantities, the best fitted parabola will be fx equals to a plus bx plus c x square. That is the best fitted parabola. So that's all. Now in the next session, we will be considering some more curve to be, we will be seeing the normal equation. Now I think you can derive the normal equation as a method. If you know, if you are aware about the method of least square, whatever the curve you require to fit over there in a bivariate data, you can move on for the normal equations corresponding to that curve. And after getting the normal equations, our target or our task is only to find the unknown quantities that we have taken in our curve, that A, B, and C, whatever the unknown quantities will be. Solving the normal equations, we can obtain the values of the unknown quantities and then put on the values, we will be getting the required curve. So we will be in our next sessions, we will be seeing some more directly, we will be seeing some more normal equations corresponding to some different types of curves that we need, that we can take on corresponding to a bivariate data as a best fitting curve. And then we will be proceed for solving some particular problems of bivariate data to fit a particular curve utilizing the method of least squares, right? So that's all for this session.